Hey, this is Mr. Clegg, and welcome to another wonderful video. Today we're going to be working with drawing motion graphs, and we're going to be doing a little calculus without the real calculus in this video, but it's a pretty good, well, you'll see. It's pretty intuitive. So first of all, I want to mention that in this video, a few things. First of all, assume constant acceleration everywhere in this packet, and that's not these are obviously piecewise functions. So there's one line from here to there. There's a different one here. There's a different one here. So those are three different sections. But within a section, you can assume that the acceleration is either zero or it's not zero, but it's constant. So assume constant acceleration. The other thing is that these graphs go together, right, as a pair, and then these two go together as a pair, and so on. All right, so it's distance or displacement or position and velocity. And the units here are in meters, and the units here are in seconds, and so on. Meters per second, seconds. Okay. So first of all, if we want to find out what the velocity is, we can find the slope of the distance and time graph. So the slope here, we go 7 meters in 7 seconds. So that's 1 meter per second. So that means we can just, and it's the same throughout the entire thing. So we can go ahead and just draw it out like that. There we go. We have a constant +1 slope. The second one I've already done here on this handout, but we're going to go from 0 to 2 seconds, so just over this time interval. We cannot, we have to do it separately later, right? So we're going 6 meters in 2 seconds, so that's a slope of 3 meters per second. So we can just go ahead and write it like that. All right, oops, trying to get this to come out right here on my, there we go. Um, there really shouldn't be a vertical line here, but I just draw that to make it easier to look at because really there's a jump discontinuity here in the velocity function, but we're not going to go ahead and worry about that. Here my slope is 0 for the rest of this, so I'm just going to go with a 0 velocity there. And I'm going to just connect these up so it's a little bit easier to see. Okay, there we go. That didn't quite come out how I wanted it, but that's right. So here we have, if we're doing the slope here, we have -4 meters in 2 seconds. So that's a slope of -2. So we're going to go here with a slope of -2 meters per second. And I'll do that one again. There we go. We're going to go here with, for the next 2 seconds, we have a slope of 1 because we want 2 meters in 2 seconds. We have a slope of 1. So we have to go up here. All right, we're going to, whoops, a little bit hard to draw with this tablet. There we go. Got a slope of 1. This one, going down, I just go ahead and connect that up so that it's a little bit easier to look at. And we have a slope of 0 from here on out, so we have a speed of 0. So hopefully that makes sense. Now, I'll leave the fourth one for you. And this is where the second level is we're going to go the other way. I already did this first one, but I'll show you how I did it. We have a -1 slope for the entire thing. So what does that mean? Well, I'm going to draw a line that has a constant -1 slope. And so it just looks like that. Um, I'm going to make this blue because I like to make displacement blue. And in my color scheme, I'm just going to go ahead and try to be consistent. So there's my blue line. There we go. And now it's the same idea here, but let's take a look. From 0 to 2, we have, from 0 to 2 seconds, we have 0 velocity. That means up here, we're going to have 0 slope in our displacement. So we're going to have 0 velocity from there to there, up to 2 seconds. Now we go up to 3 slope, which means we can have a velocity of, or sorry, 3. We're going to have a slope of 3. I can't even talk. So we're going to go for 2 seconds. So up to 4 seconds, we're going to have 1, 2, 3. We're going to go up 6. So we're going to go from 1 to 7. That means that we've got our put a dot there so I know what to aim for. I'm going to aim for that. And there we have that. And now we're back to zero again, zero slope. So that means we're not moving at this point. We're at rest again. All right. Let's do one more really quick. So we have a velocity of 2. So that means we have a slope of 2, but this one goes on for 3 seconds. So 3 seconds, we're going to go all the way up here to 7, right? So that we have, okay, so we have a plus 6 in 3 seconds. That's a slope of 2. We have 0 slope for 1 second, not moving. And then we're going to go with a -2 slope for the next 3 seconds. So -2. And let's see how 3 seconds. So 3 be negative. Oh, there we go. Is that it? I think we got that. Yeah, that looks right. Because we went negative 1, 2, 3, 4, 5, 6. Okay. So that one's crazily symmetrical, which kind of makes sense because this one is also symmetrical down here. Okay. Here's the part that oh, now we're going to do the see, right? Yeah. Now we're going to do the one where we take account of the curves. So if it's got a curve, we'll do that part last. Okay, so we'll do the straight parts first. So we're going to start with a displacement distance. All right, we have time down here. So we're going to go with a 0 slope. We have 0 slope here. Go ahead and start with that. We'll go up to the next one. I'll make little dots here so it's nice to see. We'll do this one. That's a 2 slope. So I already did this one for you. I'm just highlighting over it so you can see better and show you how I did it. And then this is the point where we go back to our assume constant acceleration everywhere in this packet, which means that for each section of the graph, there's constant acceleration, which means this is a straight line. So on this curved section here, I'm going to have a straight line. All right, I'm going to have a straight line there. So that's when I have my, there we go. That's just not cooperating. So I won't worry about the little, come on now. There. If I do it quick enough, I won't try to make it straight and move it. Second one, we have a slope of 1, it looks like. So 1 to 3, 1. So there's 2 meters and 2 seconds. So we have a slope of 1 for 2 seconds. So we're going to start here. All right. And now we're going to skip the curve part for now. We're going to go to slope of -1 for just from 6 to 7 seconds. So we're just going to go from right here, slope of -1. And in the middle, we have a parabola. And it's very important to check and see, like, if I were to make a line there, I'm trying to make a straight line, but it always shifts it a little bit when I do that. There we go. If I make a nice tangent line that only intersects that curve at one point, can you see that the slope there would be 0 right at 4 seconds, right? So that's the speed, right? So right at 4 seconds, the velocity is 0. So I'm going to put a dot here showing that right at 4 seconds, the velocity is 0. Now I'm going to connect these up with a straight line. And isn't that nice how my velocity, when it connects up there, it goes right through a point where at 4 seconds, the velocity is 0. So that's the answer to that one. All right, let's go ahead and do one more, and then I'll show you something pretty wild. Okay, so this is a 3 slope from 0 to 1. So 3 slope. There we go. We have a curve that we're going to skip. We have 0 from 4 to 7. 0 from 4 to 7. All right. And then, oh, I did want that and just straighten it out for me. Let's see. There we go. And then for this curve part, we're getting straight down like this in a straight line. Let's see if we can straighten that. There we go. Lovely. So that's our answer to that. And now I'm going to go back and I want to do page 1 again from a standpoint of integral calculus. So here it is, we're taking derivatives, right? Ooh, we're taking derivatives, what that means is we're just taking the slope of this and making it onto the graph of this. So the slope of this dt graph is the value of the velocity time graph. That's great. But now let's do this. Um, I'm going to show you how to take the integral, which is basically, it's not really, I'm not going to show you how to do the integral, but I'm going to show you how to add up the area under a curve. So here, let's take the area under this curve. Now, this isn't a physical real area because this is a velocity and this is a time. So it's not like you could have a physical thing sitting here on your desk, but there's still, you can still imagine the area under this curve. So we have 6, right? We have 6 squares here. We have 3 meters per second, and then we have 2 seconds. We have 3 meters per second times 2 seconds, right? 3 meters per second, and we have 2 seconds. If you multiply those two together, you get 6 meters. 6 meters, the seconds cancel out. And the cool thing about that is this, the area under the curve, is actually the displacement. So it now allows you to go up here. So here we go. If I have 6 and I went 6 meters. So the area under this curve is 6 meters. I went 6 meters from 0 to 2 seconds. Now, what's the area under the curve for the rest? 0. There's no area under that curve because the velocity is at 0. And so I didn't go anywhere in the rest of this. We're still at 6 meters and we just stayed there. So the total displacement for this whole entire graph is 6 meters. And there it is, 0 to 6, and we stayed right there. Let's do the first one. Here's a kind of cool thing. Let's take the area of this first little square. Okay, that area is 1. It's 1 square. 1 meter per second times 1 second gives me 1 meter, right? And look, I went 1 meter in that first second. Now let's do the next one. Now, 1 meter per second times 2 seconds, right? So that's 2 meters. Oh, look, I went 2 meters. And then another one, all right? So I can keep going. Another one, all the way up to 7, right? So now that's 7. And here's my displacement all the way up to 7. Now, this may seem like, oh, maybe that's a lucky coincidence, but it's always true, okay? And let's take a look at this one. Let's look at the third one. The area under this curve is actually negative because the curve is below 0. And you have to do the negative part separately from the positive part, right? Well, you don't have to, but for right now, we're doing it separately. So we got negative, what's that? 2 by 2, right? So that's -4 meters, because meters per second times seconds gives you meters. -4 meters. And look, 6 down to 2, that's -4 meters. We went -4 meters of displacement. Now we're going to do the next part. The area here is 2. So we went 2 meters from 2 to 4. That's 2 meters. Great. And here we went 0 meters, and we went 0 meters. So you can see really it does work all the time. It's actually always true. Very cool. All right. I'm going to skip down to this question here, okay? Now, what is the acceleration between 2 to 5 seconds? All right. I'm not going to do this whole packet. I'm just going to end on this one so you guys can do the homework, okay? What is the acceleration between 2 and 5 seconds? And then we'll get to this area thing on the second part here. So the acceleration between 2 and 5 seconds, we're going to find the slope of the velocity time graph. The slope, right? So remember, acceleration is the slope of the velocity and time graph, right? That's the slope. So we can take that second point, that's 2 meters per second, and we're going to subtract off the first point here. We're just taking the slope of this part, right? The first part, you know, so -0. So we're going to taking our 2 meters per second minus 0 meters per second. And then we will divide by the time, which is 6, right? 6 minus 2. So 6 seconds minus 2 seconds. I can't write an S. There we go. All right, so that's going to be 2 on the top, 2 meters per second over 4 seconds. So that's going to give us half, I could say 1/2, or 0.5 meters per second squared, right? Those seconds are squared. But now is the part where we get to, what's the total displacement, right? So we're taking our velocity thing, right? We kind of did the derivative, without really doing it. We took the slope of that straight line, but now we can do the integral, but all we have to do is add up the area under here, right? So we're going to take the area of this triangle, right? And we're going to add it to, maybe I'll do it in a different color here. What other color should I use? Purple. Okay. Then we're going to add it to the area of this triangle. Right? So this triangle plus sorry, I can't even talk. Rectangle plus the triangle. There we go. Let's do it like this. I'll keep the colors going. So right here we're going to do what's the area of this triangle, right? Looks like New York. Okay. Oh, I know that was bad. Okay. So what's the area of this triangle? And we're going to do plus the area of the rectangle, right? So we're going to add up what's the total displacement represented in this graph. I forgot to mention that, of course, from 0 to 2 seconds, there's no area under there, so we don't have to add anything to that. So we're going to add up these two areas, right? Okay, so let's take a look. This first triangle, right? So this is a 4, it's a right triangle. It's from 2 to 6, that's 4 seconds, right? I'm just going to use numbers. It's going to be a little bit tricky for me to see if I can move this over. There we go. The magic of computers. So we got 2. So remember, it's 2 times 4 is 8, but it's half of that, right? So it's half of the base times the height to get me the area of that. And then the area of this guy, right? It's going to move that over a little bit. All right. So this is just going to be 2 because it's 2 squares, right? So the total area of this is going to be 4, right? 4 meters. And remember, it's weird that area is in meters, but it's meters per second this way and seconds that way. So when you multiply them together, you get meters. Plus the area of this is going to be 2 meters. So the total is going to be, it's going to be 6 meters. So that's the total displacement represented in this graph. All right, I'm going to leave it there for now. I'll do the rest of the solutions in another video. All right, good luck. Let me know if you have questions and see you in the next one. Bye.